So yes, I will talk about Andreev bound states in indium arsenide aluminum nanowires. I call these weak links between these two superconductors. And Andreev states are localized quasi-particle states, localized at a coherent conductor that is connecting, bridging two superconductors. The simplest structure one can think of where we have these Andreev states is the one I'm showing you here, where this coherent conductor is just simply a zero-length single channel characterized by a transmission probability tau, here that could go from 0 to 1. In this situation, the superconductivity, when one could apply superconducting phase difference across this coherent conductor, will be locally frustrated. And as a result, what's going to happen is that the local density of states in this region, which on the bulk electrodes show the characteristic gap around the Fermi level, like I'm showing you here on the left and on the right, will dramatically change. In fact, the two discrete states will detach from the continuum, and these are the Andreev bound states. These Andreev bound states will depend on two parameters in this simple situation. One is the properties of this coherent conductor, which is just simply given by the transmission probability of electrons to go from the left to the right. And the other, of course, is the superconducting phase difference across this conductor. And this will be given by this very easy, simple analytical expression. Okay, this is the situation that we observe in atomic contacts where the weak link is just simply a single atom. And most of the experiments that we have done allows us to really account for the spectrum that I'm showing you here, the micro spectrum, which is pretty simple. You see that there is this line that corresponds to just photon absorbed at this energy. What I would like to show you today is what happened in a situation where this coherent conductor, instead of being a single atom, is an indium arsenide nanowire. And this will just modify, of course, this spectrum, and will become something that is much richer, something, well, that you could see here. This is one example. I would like to try to show you today is that there is, well, some ingredients that we could use to understand this complex spectrum. Okay, so the samples were, first of all, I would like just to acknowledge my colleagues, because this is really a teamwork. Our group in Saclay, collaborating with a theoretical group in Madrid that is led by Alfredo Levi-Iati, the group in Argentina, which is led by Leandro Tosi, and people in Copenhagen, Peter Krogstrup and Jasper Nygaard, that supply these very nice nanowires. So the sample of the nanowire we are using for fabricating these weak links are these core shell nanowires made of indium arsenide and aluminum. The initial part is a petexually indium arsenide, over which we have a complete shell of aluminum. This pretty clean interface allows us to have a well-developed superconducting gap in the system, which is on the order of 190 microelectron volts. In frequency, this corresponds to 44 gigahertz. In order to have a weak link between the two superconductors, what we do is we just etch this central part of the aluminum part, and we just expose this indium arsenide, and we put the nanowire on top of an electrostatic here gate. So this is, you could see in this side image, which is just simply an illustration, that this central part, this indium arsenide, is separated by on the order of 100 nanometers. Okay. With this kind of geometry, we can have a clean and tunable, by a voltage applied to this gate, few channel contact between these two superconductors. Yeah.
Is this coaxial nanowire going in this way that you have just indium arsenide on one side and aluminum indium arsenide on the other side? Or you etch? Did you say that you?
I just opened here a window and I just etch this selectively. Just aluminum, yeah.
And you just do it the way that it is etching the whole aluminum?
Yeah, because I mean that's the reason that this is suspended, and they just they take I don't know, just to see, but the issue is that at the end of the day we finish with this kind of structure. Okay, so the way we want to test the Andreev spectrum of this weak link, well, we just integrated this in a circuit QED setup, where you could see here this meander correspond to Landauer 4 resonator, microwave resonator that would bear with a bare resonance frequency which is on the order of 6.6 gigahertz. What you could see is that at the end of this meander, near the point where it's just shunted, the nanowire is bridging the central conductor and the ground here, and it's forming here in this region a superconducting loop. And this superconducting loop that I highlighting here in blue, if you apply a small magnetic flux threading this loop, well, you will control the phase difference across the weak link. Okay. And the phase difference is going to be just simply given by this equation. On the other side, we will control the electronic properties of this semiconducting weak link by applying here a voltage through this gate, and this will give us, well, the position in energy of the Andreev state that will depend, of course, on this gate voltage and on the superconducting phase difference. In order to, well, since the nanowire is coupled to this resonator, the occupancy of Andreev states will depend on the resonant frequency of the coupled system. And we test the resonant frequency of the system using this line that is coupled to the resonator, and by measuring here the transmission coefficient. We apply a microwave tone at the frequency F0 close to the bare frequency of the resonator. Okay. Then we have also in this setup here a bias T that allows us to apply also a microwave tone at the frequency F1, sorry, and this will allow us to, well, to induce each time this F1 hits a transition between Andreev states, well, the occupancy of the Andreev state will change, and this can be detected, and in this way we construct the absorption spectrum of the system. So in fact, the signal that we send for the readout is amplified here, and we measure the two components, in phase and out of phase, of this transmission coefficient. And when we, as I said before, when the frequency of this tone hits the transition between the Andreev levels, what we are going to see is that the in phase and the out of phase part will change. So let me show you once again what we typically observe. So all the experiments I'm going to talk about are done at low temperatures in the order of between 10 to 30 millikelvin. Okay, and this is the spectrum between 2 to 25 gigahertz. So well inside the superconducting gap of aluminum. Okay, and what you could see is that besides that it's pretty rich, we have, and if you change the gate voltage, you're going to have something which is really different. You conserve anyway some general features that I'm highlighting here in green, in blue, and red. In green, what you see is that there are bundles of lines that are crossing at delta equal pi and delta equal 0 or 2 here. This is bundles of 4 lines. And what you can see also that there are lines where the minimum is around delta equal pi. So let me now just start by giving some ingredients to understand how we could explain these generalities we observe in the Andreev absorption spectrum. And for that, we have to consider what we have as a system. So what you can see here is that in gray, I'm just schematizing the superconductors, and this green part corresponds to the normal region, to the nanowire. Let me say that we have to distinguish, two limiting cases, the weak and the strong contact limit. In the weak limit that I'm just showing you here at the top, corresponds when you have between the superconductor and the normal region tunneling contacts. And in this case, electrons will be confined in the central region, and we have to consider Coulomb interaction that are pretty large. And this situation is, in general, described by this kind of model. It's a superconducting version of the Andreev model. You have here a quantum dot, and this is what Sergi just showed us before, and also Ruben was discussed in their talks. Okay. The situation that we will choose for us describe better what is happening in indium arsenide is this one, where we have good contacts. And when you have good contacts between the superconductor and the normal region, there is a process that has a probability equal to 1 for electrons that have an energy smaller than delta. So these electrons cannot enter into the superconducting part as such, and what they can do is just use a process that is known as the Andreev reflection process, where what happens is that the electron will just pick up a partner below the Fermi C and just form a Cooper pair on this part due to just the pairing interaction that we have in the superconducting part. Doing so, they let a hole behind that will travel in the opposite direction towards the other interface on the right. So this Andreev process will also take place in this left interface, and the hole will be converted into an electron, and this along this journey, if these back and forth reflections are coherently constructed, like if we have is a kind of Fabry-Perot with these two mirrors at the superconductors. Well, in this situation, we're going to have the most of this cavity will be the Andreev bound states of the system. Okay, so it's a kind of Fabry-Perot, but in order to get the energy of the states that we have here, well, we have to consider what is the phase accumulated during this journey by the electron and the hole. Okay, and this has two parts. Well, one which is linked to the phase that is acquired by the electron that forms this Cooper pair and is reflected as a hole, which is the superconducting phase on the right electrode, and this part that depends on the energy of the electron, the energy divided by the superconducting gap. There is also the one that is associated to reflection on the right, but also because the electrons and holes are just propagating along this central part, there is this phase that depends on the wave vector of the electrons and the holes. And this is this term KEL and KHL. We can write these two terms using adimensional variables, and these two terms will give us this propagation phase can be written by these two terms. Is equal to 2i's lambda over E, where epsilon is the ratio between the energy of the electron and delta, and lambda is the ratio between the size of the weak link and the coherent length that in the ballistic limit is equal to the Fermi velocity of the electrons and the superconducting gap of the reservoir. So it's a kind of hybrid superconducting distance, okay? And the constructed interference means that along this journey you have accumulated a phase equal to 0 to pi. And it's given by this transcendental equation, okay? This is the explanation of the Andreev states for the right movers electrons. And note that in this process, you are transporting a Cooper pair from the left to the right. So these states are transporting the supercurrent. So this is at the origin of the Josephson effect in these systems. And okay. You have also the left movers. I mean, just simply the ones that move in the opposite direction. The equation, the transcendental equation, is slightly different. And this gives rise to these states that will depend, the number of which will depend on this lambda, the ratio between the length of the weak link and the coherent length. If you are in the short limit, you have two states, and we've increased little by little. We are more and more states that enter into the, wow, okay. So I will have to well, sorry. So this, but let us consider what happened in the indium arsenide nanowire. Because in the indium arsenide nanowire, we don't have only, we have a confinement in this direction. So we're going to have a subbands in the system, and this will be the Hamiltonian to describe the nanowire. And what you see is that due to the spin orbit, you are splitting these subbands, okay, in spin up and spin down. And this term in the Hamiltonian will just couple the system here at with the spin up and spin down of different subbands, and will just lift the degeneracy at this level. Now, to understand what we have observed, just simply we are going to consider that the chemical potential is here, and although we have a single band occupying the system, what you see is that the Fermi velocity associated with different spin texture is different. And this is the main issue, okay? In this particular case, what happened is that we have already the right movers and left movers that we have in a finite weak link. But this corresponds to the spin, let's say, spin up here. But you have, because the Fermi velocity is different, we have also a series of one associated to the other Fermi velocity. And due to the fact that if you have some scattering here in the nanowire, if you consider this, what happens is that this loop that with the left and right movers will be just coupled. And when they couple, at this point, well, there are just avoided crossings that are going to take place. And this gives us this particular Andreev spectrum that you could see leave the degeneracy, the spin degeneracy, except at the points delta equals 0 and delta equals 0 and delta equal pi, due to time reversals. Okay, so once we have this Andreev spectrum, it's really relatively straightforward to see that if you fix for example, if you have too many folds and you fix the phase here, well, you could have pair transitions that, you could have pair transitions by exciting, breaking a Cooper pair and putting on, or in the lower manifold or in the upper manifold, or mixed transitions that will give rise to these red lines, okay? But you could also, because any superconducting circuit, you're going to have out of equilibrium quasi-particles. Quasi-particles just can drop in one of these states, and would you just could have also this single particle transition that there is not that is not changing the number of quasi-particles in the system. Here, I mean, I just forget to say that in this experiment, you are not changing the parity, okay? So you could just change, just create two quasi-particles, or you could just promote a single quasi-particle that was trapped in a single state. So this just allows us to identify this in the low energy part, this structure of 4 lines crossing at 0 and pi with the different transitions between these two manifolds. These are intermanifold with the spin conservative transition. The outer ones, the inner ones correspond to the spin fleet transition. And you could see if you perform the difference between these two spline curves, you're going to get the red ones that correspond to what you observe in the lower region. Okay, that's for this. The pair transition for us is going to correspond to this, but what are these transitions in blue? In fact, what you see is that if you follow for example, at the given flux where we see this lift this degeneracy, we follow the lines. What you could see is this pair transition and these blue lines that we are not understanding what they are in phase. So it's mostly, it seems to be a pair transition in the case. But you see that there are also something that is pretty irregular, that you see that there are three lines that run together and a line that goes a little bit up, right? And we think that this characteristic could be related to the fact that probably what we observe here in the middle, are mixed transitions, but they are not described by this model I presented you, which is in the midfield approximation. Probably we had to take into consideration Coulomb interactions. And the reason of that is that if you see, now we create two quasi-particles. These quasi-particles could be in a triplet or in a singlet state. In the triplet state, they will be separated spatially. And in this case, we expect that the three lines corresponding to this triplet are going to have less energy, cause less energy in transition than the singlet one. This could be an explanation, but to go further, we just, with our colleagues in Madrid, they just do a model that considers here, some ingredient. This is a tie-binding model where we have these three chains correspond to the three different channels. I'm finished with this. And the number of sites in this direction allows us to emulate the fact that we are a finite length weak link. And using the parameters that allows us to get the spectrum, what you see is the following. Sorry, the main issue is that we consider here so the impurity, so the scattering process, but also a term of a Hubbard term that will allow us to emulate the Coulomb interaction in the system. Okay, this is the most important thing. Okay, once we could just do these simulations, and you see when this charging energy effective charging energy is 0, you recover these lines in green. This red line would correspond to the pair transition of the lower manifold, and these lines that correspond to the mixed transition. Okay, but as soon as you have this Coulomb interaction, you see that there is a lifting of this degeneracy at 0 and pi. And if you go further, you could see that what we have observed in the experiment is pretty close to what they have calculated. Okay, with this I would like just to end and to say, these are just to wrap up. I have shown you a microwave spectrum of the indium arsenide nanowire weak link. We have observed that the spin can be, we could have Andreev states that are spin split even at magnetic field equal to 0. This is due to three ingredients: the Rashba spin orbit coupling, the fact that we are in a finite length weak link, and the confinement in the direction of the nanowires that allows us to have more than a subband. And we have observed also that even in the case that we have a really a very transparent interface between the superconductor and the semiconducting material, Coulomb interaction can also appear and just slightly modify what we have observed in the experiment. Okay, with this I just finished, and thank you for your attention, and just wait for the questions.